computer program, otherwise known as software, is made up of ones and zeros. This is known as binary, and it is the only thing that the computer understands. So how do we get from an idea to the finished software? Writing the binary yourself would be slow, tedious, and take way too long. Instead, we'll use something called source code. Source code is the instructions to the computer that is meant to be human readable, with a little practice, that is. Source code can be written in one of many different programming languages. These are the main ones in use today. Here's a very simple program written in a programming language called C++. This program simply displays the words "Hello World" to the computer screen. In order for the computer to actually run the program, the source code must be turned into binary. This process is called compiling. Once we have our ones and zeros, the computer can then run the program. If there are any mistakes in the source code, such as a misspelled word or missing punctuation mark, the compile will fail and you won't be able to run the software. Simple programs can be written by one developer in a reasonable amount of time. However, professional software may involve hundreds of developers and take a matter of years to complete. A large software project like this would be split up into hundreds or even thousands of files. Being able to collaborate is essential for their success. One concept that allows them to do so is called revision control. Here's how it works. All the source code for the software is stored on a server. Each developer stores a copy of these files on their machine. They can then make changes to one or more files and then submit those changes to the server when they are ready. The server stores a detailed list of what files were changed, what those changes were, and who submitted it. If at any time the program gets into a bad state, the developers can undo the changes until the program is working correctly again. Software developers try hard, but there are always a few problems with the code. We call these problems bugs. Even after a piece of software is released to the public, the software developers must continue to fix bugs and further improve the software. This is why software has updates or new versions that come out periodically. Software can be created in two different ways. The most common is proprietary. The software is owned by a person or company and sold to make money. The source code is not released to the public, only the finished product is. Anyone wanting to change the software will have a difficult time without the source code. The second approach is called open source. This usually means the program is free and that anyone can get access to the source code. You might be surprised to learn that many of the programs you already use are also open source. Many times the developers are volunteers who are passionate about the software they are creating. Oftentimes they don't even get paid. The software may be free, but keep in mind that donations are rarely turned away.
How you do things. We call this procedural knowledge, or knowing how. And when we write down procedural knowledge, we end up with what's called an algorithm. An algorithm is a sequence of instructions for how to do things. Throughout history, we've communicated our know-how through storytelling. At first, these stories were shared orally. Starting with the earliest forms of painting, people depicted stories as images of things happening across time. At first, we did this with picture sequences, and later, letter sequences. But we can think of the key stages in a story as steps. And this is the basis of algorithmic thinking, the ability to break how we do things into a step-by-step procedure. In the most basic form, an algorithm is just a linear sequence of steps, a single pathway of action. But now think of something more complex that you do, which can't be easily expressed as a simple list of steps. When you try writing down the steps for how you do these complex things, you'll notice you won't follow the same linear pathway each time. There is a conditional future. Practically, this means the word if will pop up in your list of steps. Every time we say if, it means our pathway of action will branch into possible futures. No matter how far back you look in our written records, you will find if-then pairings used to describe our knowledge about the world. Early records of omens were messages from the gods about the future. For example, in ancient Greece it was believed that the gods made decisions in an assembly concerning the course of the world's affairs and the fate of human beings. And they delivered these predictions about the future in the form of omens. For example, they are typically structured as if, followed by a sign in the natural world, and then, followed by the resulting event. Across cultures, ancient documents have been discovered which contain lists of omens that people could consult to better understand the fate of their lives. And they can be viewed as an early form of science, or proto-science, an attempt to describe the world. So it's these if-then statements, or what we call conditional statements, that will help you define the complex things you do. And with that, we have everything we need to define algorithms. Algorithms are, 1, a sequence of steps, and 2, these steps can contain conditional statements. And you can describe anything that is describable using just these two concepts. No matter how an algorithm is run, a human actor following instructions or a computer following machine code, at some level, it's understood to be following discrete steps, resulting in a pathway of execution. And each step in this pathway takes some amount of time. So the expected number of steps it takes a process to finish defines the time resource or time complexity of an algorithm. And while a machine or human is following or running an algorithm, it may need to store or retrieve information which must be recorded in memory. And memory, no matter the form, takes some amount of space. For example, when you follow the steps in the algorithm for multiplication or long division, at certain steps you need to write down extra numbers that allow you to arrive at the answer. These extra numbers are the memory resource of those algorithms. And the total amount of memory needed, measured as the number of symbols, defines the space resource, or space complexity, of an algorithm. So when we run any algorithm, no matter what it describes, it results in some pathway of action. And in the modern study of algorithms, we always come back to two big questions. 1, how much time and space does it need? And 2, how can we be sure that the output of our algorithm is correct? Because anytime we hit a conditional statement, before we can take our next step, we'll need to confirm at some level if something is true or not. But how do we ever really know if something is true or false? And this requires some form of logic.
What is an algorithm? One definition might be a set of steps to accomplish a task. You might have an algorithm for getting from home to school, for making a grilled cheese sandwich, or for finding what you're looking for in the grocery store. In computer science, an algorithm is a set of steps for a computer program to accomplish a task. Algorithms put the science in computer science. Something about existing algorithms. You can save yourself some effort and make your programs faster by applying the right one. So what makes a good algorithm? The two most important criteria are that it solves a problem and that it does so efficiently. Most of the time, we want an algorithm to give us an answer that we know is always correct. Sometimes we can live with an algorithm that doesn't give us a correct answer or the best answer because the only perfect algorithms that we know for those problems take a really, really long time.
What's an algorithm? In computer science, an algorithm is a set of instructions for solving some problem, step by step. Typically, algorithms are executed by computers, but we humans have algorithms as well. For instance, how would you go about counting the number of people in a room? Well, if you're like me, you'd probably point at each person, one at a time, and count up from 0. 1, 2, 3, 4, and so forth. Well, that's an algorithm. In fact, let's try to express it a bit more formally in pseudocode, English-like syntax that resembles a programming language. Let n equal 0. For each person in room, set n equal to n plus 1. How to interpret this pseudocode? Well, line 1 declares, so to speak, a variable called n and initializes its value to 0. This just means that at the beginning of our algorithm, the thing with which we're counting has a value of 0. After all, before we start counting, we haven't counted anything yet. Calling this variable n is just a convention. I could have called it most anything. Now, line 2 demarks the start of a loop, a sequence of steps that will repeat some number of times. So in our example, the step we're taking is counting people in the room. Beneath line 2 is line 3, which describes exactly how we'll go about counting. The indentation implies that it's line 3 that will repeat. So what the pseudocode is saying is that after starting at 0, for each person in the room, we'll increase n by 1. Now, is this algorithm correct? Well, let's bang on it a bit. Does it work if there are 2 people in the room? Let's see. In line 1, we initialize n to 0. For each of these 2 people, we then increment n by 1. So on the first trip through the loop, we update n from 0 to 1. On the second trip through that same loop, we update n from 1 to 2. And so, by this algorithm's end, n is 2, which indeed matches the number of people in the room. So far, so good. How about a corner case, though? Suppose that there are 0 people in the room, besides me, who's doing the counting. In line 1, we again initialize n to 0. This time, though, line 3 doesn't execute at all, since there isn't a person in the room, and so n remains 0, which indeed matches the number of people in the room. Pretty simple, right? But counting people one at a time is pretty inefficient too, no? Surely we can do better. Why not count 2 people at a time? Instead of counting 1, 2, 3, 4, 5, 6, 7, 8, and so forth, why not count 2, 4, 6, 8, and so on? It even sounds faster, and it surely is. Let's express this optimization in pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. Pretty simple change, right? Rather than count people one at a time, we instead count them 2 at a time.